Alright guys, today I'm going to go through optical isomerism. This is a nice and quick chapter, but before we go ahead I just want to mention that nomenclature is mentioned in the spec point as well in 3.3.7 if you follow the AQA syllabus. However, I've just skipped it because I think personally the best way to remember the compounds is when you actually learn about the compounds and practice doing exam questions and stuff. Okay. Now if you think back to year 1, you guys went through geometric isomerism. Now this is a type of stereoisomerism, and if you just remember the definition, it is a compound with the same structural formula but have a different spatial arrangement of atoms. Okay, so in year 1 what this meant was like these both have the same structural formula. Okay, so if I was to write the structural formula for these, it would be C2H5, CH3, CH2, C, OH, C, H, CH3. Okay, so this is the structural formula for both these compounds, and they both have the same structural formula. Okay, however, if you notice, these atoms are arranged differently. Okay, and we went through why in the alkenes topic. Okay, so this is an example of stereoisomerism. Okay, because it has the same structural formula but different spatial arrangement of atoms. Okay, now another type of stereoisomerism is optical isomerism. Okay, so optical isomerism occurs in carbon compounds with 4 different groups of atoms attached to a carbon. This carbon is called an asymmetric carbon. So in this example, this is an asymmetric carbon. Okay, it's also called a chiral carbon sometimes. Okay, most of the time actually it's called a chiral carbon. Now what makes it a chiral carbon is the fact that it has 4 different groups attached to it. Okay, so 1, 2, 3, 4. Okay, now if for instance we had something like this, CH3, H, OH. Now this would not count as a chiral carbon over here. Okay, now the reason for that is that you have 2 methyl groups. Okay, so the definition is 4 different groups. Okay, so none of the groups can be the same. Okay, and you may be thinking in this diagram, well, we've got 2 carbons connected to each other, right? But you're looking at the group as a whole. Okay, so because of that, you would count this as methyl group, and this is an ethyl group. Okay, so they're 2 different groups. Okay, now here I've drawn a compound, and what I want you guys to do is pause the video and try to see if you can spot all the different chiral carbon atoms. Okay, so remember, when you have a chiral carbon atom, you have 4 different groups attached. Okay, so let's see each carbon atom. So here, for this one, you have 2 hydrogens, right? So that's not 4 different groups. So this one is not a chiral carbon. Here you have 1 group here, you have another group here, you have another group here, and you have a 4th group in here. Okay, so this one is a chiral carbon atom. Okay, now here, now you have a double bond, right? One of the carbon atom has a double bond. Immediately when it has a double bond, you know it's not going to be a chiral carbon, because you can only have a maximum of 3 groups then. Okay, but you need 4 different groups. So this one is not a chiral carbon. Same thing with this one, because it's attached to a carbon atom with a double bond as well, the same one. So it has a maximum of 3 groups. So this one is not a chiral carbon. This one has a double bond as well, so it's not going to be a chiral carbon because it has a maximum of 3 groups. This one has 1 group here, 1 group here, 1 group here, and another group here. So it has 4 groups, therefore it is a chiral carbon. Okay. This is a harder type of question. Okay, so pause the video and have a go at it yourself. Okay, so as we know, we're looking for carbon atoms with 4 different groups attached to it, okay? So the way I would go about this first is identify the carbon atoms, okay? So we just notice these little corners here. Okay, and then the next thing we're looking for are ones with 4 different groups, okay? But we know that not all the groups are drawn because in the skeletal formula the hydrogen groups aren't drawn, okay? So I think it'd be easier if we draw all the hydrogen groups. So for this example, we know there's no hydrogen group because you have 1, 2, 3, 4 bonds, okay? And carbon can only bond 4 times, so I can't fit any more hydrogens. However, if I was to go to this carbon here, okay, I have 1, 2, 3 bonds, okay? So I can fit on another hydrogen. Okay, same thing here, I can fit on 2 more. 2 more here. None there. 1 more there. 2 more here. None there. 2 more here. None there, okay? Now I need to look at the carbon with 4 different groups, okay? So this one has 1 group, 2 group, all of this, and 3 groups, okay? So, but you need 4 different groups. So this one is not a chiral carbon, okay? Now this next one has 1 group here, 1 group here, another group here, and another group here. Okay, so this can count as a chiral carbon. Okay, so this is correct. This one has 2 hydrogens attached to it, so it can't be chiral carbon. Okay. Same thing with this one. This one only has 3 groups attached to it. This one has 1 here, a second one, a third one, and a 4th one, okay? So this one does count as a chiral carbon. This one has 2 hydrogens, so it doesn't count. This one only has 3 groups, so it doesn't count. This one has 2 hydrogens, so it doesn't count. This one has 3 groups only, so it doesn't count. So now we have our chiral carbons. I'm just going to circle them like they asked. Okay. Now, why are these compounds specifically classified as stereoisomers? Okay. Well, these compounds have the 4 groups, and these 4 groups can be arranged in tetrahedral shapes, okay, around the carbon atom. This causes 2 different isomers that are not superimposable to be formed, and they are mirror images, okay? So these 2 compounds that are optical isomers of each other are called enantiomers. Okay, so basically what this all means is when you have a compound with a chiral carbon atom like this, okay, the 4 groups around it can be arranged right in a tetrahedral, and essentially you can have a different orientation. Okay, so you can have something like this, or you can have something like this, and these 2 compounds have a different orientation. Now this whole thing is really important, because in an exam they'll sometimes give you one enantiomer like this, and then they'll ask you to draw the other enantiomer. So what you do is you draw the mirror line there, and then you just draw the mirror image of it, okay? Now, what does non-superimposable mean? Well, for example here, this is our mirror image, right, like we had before. And notice how, since the mirror images, they don't have the same orientation, okay? And to prove that, we can rotate this molecule on the right that way. And when we do that, this moves right around here, this moves over here, this moves over here, okay? Like that. So now we've rotated it to the right, okay? And notice so the blues match up and the reds match up, but the yellow does not match up to the same spot, and the green doesn't match up to the same spot, okay? Therefore, they do not have the same orientation, and that's what not superimposable means, okay? You can't rotate one to make it look like the other one, okay? Optical isomers have similar physical and chemical properties, but they rotate plane polarized light in different directions, okay? One enantiomer rotates it in one direction, and the other enantiomer rotates it by the same amount in the opposite direction, okay? What this really means is, so if you have light, okay, light normally flows in different directions, okay? So you have light coming like this, but some of the light will be going, some of the light will travel in this direction, some of it will travel along this plane, okay? And then, but when it goes through the polarizer, okay, only one plane of light is left, okay? So this light, okay? Now when it goes to a sample of an optical isomer, the light actually rotates, okay? So it goes in that direction by a certain amount, okay? And now it travels in like this, okay? Now what's really cool is that if you have an enantiomer of this isomer, then the enantiomer will rotate the light by the same amount but in the opposite direction, okay? So now it will be traveling like this, okay? So the enantiomers have opposite effects, okay? One will rotate it clockwise and the other one will rotate it anti-clockwise, but by the same amount, okay? A racemic mixture is a mixture of equal amounts of the two optical isomers, and it will not rotate plane polarized light. Now, the reason for this is that if you have one enantiomer and it rotates the light this way, then the other enantiomer rotates light that way, okay? So overall, there's no effect because they cancel each other out. A racemate will be formed in a reaction mechanism when a reactant or intermediate has a trigonal planar group in the molecule and is approached from both sides by an attacking species. Okay, so for example, if you have something planar, it means it's flat like this. Sorry, 1 second. Okay, so if you have something planar, it means it's flat like this, and your intermediate can either attack from this side or this side, okay? And the side that it attacks on will affect which enantiomer it is, okay? Now, here's the thing, it has a 50-50 chance of attacking either side, and that's why there will be equal amounts of each enantiomer, okay? And then if that happens, a racemate is formed, and you would have no optical activity, no overall rotation of the light. Okay. So this is the mechanism you guys have gone through, which actually forms optical isomerism. It's electrophilic addition. Okay, I just wanted to show you guys a 3D description of what this looks like. So here we have our trigonal planar molecule, and so basically it can either get attacked from this side or this side, okay? And whatever side it gets attacked by affects which enantiomer it forms. Okay? Drug action and optical isomers. Drug action may be determined by the stereochemistry of the molecule. Different optical isomers may have different effects. Okay. So here we have thalidomide. One enantiomer of thalidomide causes birth defects in unborn children, whilst the other has useful sedative problems. Unfortunately, it was given in a racemic mixture when first used. So basically, in medicines, they have to make sure they have the right enantiomer, because one enantiomer could have a negative effect, and the other one could actually be really useful, okay? But you only want to have the useful one which is a problem sometimes, especially when like a racemate mixture is formed. You need to separate the two. Okay, time for an exam question. Okay, the product of hydrolysis of 2-bromobutane is butanol. Both molecules are chiral. Okay, state what is meant by the term chiral using 3-dimensional diagrams of the enantiomers of butanol. Illustrate your answer. Okay, so what I'm going to do first is I'm going to draw the tetrahedral structure of one of the enantiomers, okay? So, remember, for your tetrahedral, you need to draw the dotted line, the big wedge line, like this, and 2 straight lines. Okay? C2H5, okay? So this is butanol, the tetrahedral. Now to draw the enantiomer, okay, I'm going to do a mirror line, and then I'm just going to draw the mirror image, okay? OH. Okay, actually, you know what? If I to the left, H. Now, this is a pretty badly drawn tetrahedral. Okay, and that's your first part done. And then state what is meant by the term chiral, okay? So chiral means the compound, a chiral carbon atom with 4 different groups. Groups attached to it. Just to get all the marks, I'm just going to say forms isomers which are non-superimposable. Okay, so forms. Now in an exam you don't know what the marking points are, right? Exactly. So I'd say try and over-inform. Okay? Just in case. Unless you're short on time. Okay? Now, this is probably more than you need, but it has, just in case, like I said, all your marking points. Okay? Now let's see. Okay, so you get a mark for each of your enantiomers, and then forms isomers which are non-superimposable. Okay, allow chiral carbon which has 4 different groups attached. Okay, so either one. You don't have to say both, but I think it's good to have it just in case. Okay, here's another exam question. So state the meaning of the term stereoisomers. Okay, so they have the same structural formula, different spatial arrangement of atoms. Okay, explain how a pair of stereoisomers can be distinguished. Okay, so now if you think back to our concept with the plane polarized light, okay, we know one enantiomer will rotate it in the clockwise direction and the other one will rotate in the anti-clockwise directions. So we just say rotate plane polarized light in opposite directions by the same amount. Okay. The sample of X produced consists of a racemic mixture. Explain how this racemic mixture is formed. Okay, now if you think back to our planar group, the nucleophile or attacking species can attack from either side with a 50-50 chance. Okay, so let's just write that down. Okay, so that should get you all your marks for the question.